Hello and welcome to this quick review of amines, which obviously needs your completed independent study materials and notes ready in front of you before we start. And we'll focus on aliphatic and aromatic amines with a view on structure, naming, basicity and synthesis. So the amines as a functional group or an homologous series are analogous, that is to say similar, to ammonia in that one or more of the hydrogen atoms in the ammonia molecule have been replaced by an alkyl group or benzene ring. So the examples you can now see show how amines are very similar in their structure and layout to ammonia. A very important part of the functional group is the fact that it's got a lone pair on the nitrogen atom. So we'll bring this up a little bit later in the clip, but it's very important to not lose sight of this. So amines can be classified as primary, secondary or tertiary according to how many R groups are bonded directly to the nitrogen atom. So for our purposes, an R group can be taken to be any length or size of a carbon chain or ring. So let's apply this idea to the amines in the screen. So taking the simple examples on the screen and an R group to be CH3, in this particular example, that would make methylamine a primary amine, dimethylamine a secondary amine, and trimethylamine a tertiary amine. If you add 4 groups to the nitrogen, in other words the lone pair becomes involved in a dative covalent bond, you get what's called a quaternary ammonium ion. And because the lone pair is no longer a lone pair as such, it's now a bonded pair, it's not able to behave in the same way as an amine. So it's called a quaternary ammonium ion, and you'll notice on the example I've done that the nitrogen becomes positively charged. If you start mixing the different groups on the nitrogen atom, you will change the name obviously, but not the classification unless the group reverts to a hydrogen. So let's have a look at some examples of that. So changing some of the groups around now gives us new names, but the same classifications as before. Obviously, if you were to swap some of those groups for hydrogen atoms, that would change the classification again. I've also inserted a benzene ring in the form C6H5, which is its structural form, in the first amine on the left, just to highlight how that is now an aromatic amine. If you get two different groups, two different alkyl groups for example, attached to the same nitrogen atom, the larger group forms the main part of the name. So if we take the one towards the top of the screen, the ethylamine is the main part of the name. The reason for this is the ethyl group is the largest group attached to the nitrogen, so the other smaller group is said to be N-substituted. So in this case the methyl group is the smallest out of the two groups, so it's called N-methyl ethylamine. So if you look at the other one, the bottom right hand corner, you've got 3 possible groups. I've chosen the largest group as propyl group and based the name on propylamine. So N-ethyl, N-methyl, alphabetical order, and then propylamine. Okay, so let's summarise what we've covered so far. So running through them really quickly, amines can be primary, secondary or tertiary depending on the number of groups attached to the nitrogen atom directly. To be an amine, the nitrogen atom must still have its lone pair of electrons for the molecule to be considered an amine. If a fourth atom then bonds to the nitrogen by dative covalent bond, we then get a quaternary ammonium salt or a quaternary ammonium ion with the nitrogen atom possessing a +1 charge. When you get multiple alkyl groups of the same type, you get di and trialkylamines. Multiple alkyl groups of different types mean you have to decide which one is the largest, and that forms the main part of the amine's name. So let's have a think about this. Pause the clip with these naming and classification rules up on the screen and try to name and classify the structures in red at the bottom of the screen. So hopefully you came up with these names: N-methyl diethylamine, NN-dimethyl diethylammonium bromide and NN-dimethyl methylpropylamine. Now you'll see in the box at the bottom I made these quite difficult on purpose. If you're not sure, you might want to jot them down and check them with your teacher if not sure, and then we can have a look perhaps at the structure and the displayed formula so you can start to get your head around it. But without getting too tied up in the naming, because naming usually isn't going to be a lot of marks, maybe 1 mark or 2 if it's a particularly tricky one. It's important to cover it, but not to get obsessed by it, obviously. So what we'll do now is move on to the reactions of amines. So all amine chemistry is based on the ability of the nitrogen atom to donate its lone pair to a dative covalent bond. If it does this with a proton, then it's behaving as a Brønsted-Lowry base. So if we take from first year chemistry the way that ammonia acts as a base to form NH4+ for the ammonium ion, we can do the same for methylamine, we can do the same for dimethylamine, and also trimethylamine acting as a base. As you add extra alkyl groups to the nitrogen atom, substituting for the hydrogens, what they do is they donate electrons along the covalent bond to the nitrogen atom, so therefore making the lone pair a little bit more available for donation. This means that as you go from methylamine to dimethylamine to trimethylamine, this effect is increased, so you get increasing basic behavior, increasing basicity. So the identity of the alkyl ammonium salt produced depends on the acid used as well as the amine that is reacted in the first place. So if the acid was HCl, can you name the salt that would be produced here? So I want to pause the clip at this point and see if you can work it out. So hopefully you got these 3: methylammonium chloride, dimethylammonium chloride and trimethylammonium chloride. So if we consider the basicity of phenylamine, we've got to go back to the structure of phenol from before. So phenol is covered in a separate clip, and if you're doing this in class, a separate lesson. But the ideas are quite similar. So starting by drawing out the whole structure, as if you were going to start doing it for benzene, we can put in the p orbitals above and below, the carbons and the nitrogen. So as the lone pair in the nitrogen is delocalized into the pi system, so what happens as a result is the lone pair is that was on the nitrogen is less available now to form a dative covalent bond with an incoming proton. So phenylamine is less basic than its aliphatic counterparts. So the final part of the clip is going to cover the preparation of both aliphatic and aromatic amines. So when you're looking at the preparation of amines in general, there's actually 3 different chemical pathways to learn, so I'll cover each one in turn. So the first stage in the production of a primary amine is to use a haloalkane reacting with NH3 via nucleophilic substitution to give an alkyl ammonium salt. So the alkyl ammonium salt reacts with an alkali in a second reaction, second stage, to form the primary amine, salt of the alkali and water. So there's a couple of conditions that you need. It needs to be carried out in ethanol, not water, in order to prevent H2O substituting instead of NH3, and it's got to be carried out in excess NH3 because this prevents further substitution of the amine group. Now what would happen if you didn't have excess ammonia is you'd get your product acting as a nucleophile and going back and doing further substitutions. You don't want that to happen, so we have excess ammonia to prevent that taking place. So when you're making secondary and tertiary amines, you allow the further substitution to happen. So the primary amine goes back and substitutes again with the haloalkane, which is the first reaction on the left. So that gives us a quaternary ammonium salt again, but this one is a secondary structure, a secondary amine structure that led to it. So that salt can react with NaOH in the same way that we did it for primary amines, which gives us a secondary amine. Now that can also go back and do the same thing with RCl a third time to make a tertiary amine. But unfortunately, as you can see, I don't have enough room to put that in. It would start to crowd the screen a little bit. So maybe you might want to pause the clip and try and think about the equation that might work for that. I don't know. So the final part of this review of amines is a quick look at how we make aromatic amines. So this time we reduce nitrobenzene with tin and concentrated HCl. So not forgetting that reduction can also mean the addition of hydrogen in organic chemistry. So the NO2 group in nitrobenzene becomes NH2. So looking at the equation, a really easy mistake to make is to put the wrong number of hydrogens in, as in just put 2 in because you're using 2 to make NH2. What you've got to do is think about how many oxygens you're taking off. So NO2 is 2 oxygens. So that requires 4 hydrogens to turn 2 oxygens into 2 waters. So therefore what you're doing is you're combining the H2 on C6H5NH2 with the 2 lots of H2 in 2H2O. So 6 hydrogen atoms are needed. Don't forget the H in a square bracket means hydrogen atoms provided by a reducing agent, in this case the tin and concentrated HCl. You can write tin and concentrated HCl reflux above the arrow at your reaction conditions because they're likely to ask you about this as well. So it's also important to point out that in the same way it happened with secondary and tertiary amines, we also use an alkali, because what you get, first of all, is a phenyl ammonium salt, or a phenyl ammonium ion, C6H5NH3+, which is not phenylamine. So to get the phenylamine in the equation, you have to react that further with NaOH to give the final C6H5NH2 that we're looking for. So it's similar to the 2 highlighted reactions that we talked about a few minutes ago, except this time it's an aromatic amine we're looking at, not an aliphatic amine. So as always, it's time to go away and practice some examples now to get your head around all of this. But in the meantime, thank you very much for listening, and until next time, see you soon.